So we're going to do some differentiation from the definition of the derivative examples. Let's start with f of x equals 1 over x. So f prime of x equals the limit as h goes to 0 of 1 over x plus h minus 1 over x over h. Just using algebra, we know that we need a common denominator. So the numerator should equal x minus x plus h all over x times x plus h over h, which of course equals the limit as h goes to 0, again with more algebra, of x minus h, so minus h is in the numerator. And then we combine these denominators by rules of algebra, right? With the idea that a over b over c equals a over b times c. So this equals h, x plus h. And now, at this point, we can cross out the h's. They cancel each other out because h is not equal to 0. And that's the beauty of the limit. So finally we have the limit as h goes to 0 of 1 over x times x plus h. Now we can just substitute for h. Again, x is not equal to 0 because f is not defined when x equals 0. So we can plug in 0 for h and we get negative 1 over x squared. All right, so let's see if that checks out with what we know the derivative should look like. This is what 1 over x looks like. Notice that the derivative, in other words, the slope of the tangent line, is always negative, 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 negative. Right, these are negative slopes. And negative slopes which are going to 0. So the graph of negative 1 over x squared coincides intuitively, geometrically, of what the derivative of 1 over x should be. All right, let's do another example. Let's do f of x equals radical x. So again, we have the limit as h goes to 0 of radical x plus h minus x over h. At this point, oops, there should be a radical here. At this point, we want to clear the radicals. In other words, get rid of the radicals. And again, from algebra, we know that we can multiply by the conjugate to do that. So let's multiply x plus h minus radical x over h times radical x plus h plus radical x plus h plus radical x. So now, in the numerator, we've now multiplied this term times this term to get x plus h minus x in the numerator and h times this denominator with radicals. This is good because now we can eliminate x, which leaves h in the numerator, h in the denominator. We can cancel those, and now we have limit as h goes to 0 of 1 over radical x plus h minus radical x. And now, as long as x does not equal 0, we can just simply now plug in h equals 0 because there's no problem with 0 being the denominator. So that just equals 1 over 2 times radical x. And again, let's see if that coincides with our intuition of what the function should look like and what its derivative should be. Radical x so let's draw the derivative underneath it. Notice this is an increasing function. All right, so we have a positive derivative, but the derivative is decreasing to 0, which coincides with this. It's positive, positive, but decreasing to 0. So this geometric interpretation of the derivative coincides with what we computed algebraically.